Today's session is Color Management Fundamentals. It is my pleasure to introduce our speakers for today. Carrie Maloney, Field and Channel Marketing Manager for Fiery Wide Format, and John Nate, Worldwide Technical Products Training Manager for Fiery Wide Format. So with that, let's begin. Carrie, please take it away.
Thank you, Yael. Okay, so on today's session, we will cover color management fundamentals, including basic color theory and color management terms. As most of you are aware, the benefit of color management is predictable and consistent color results in less time with less waste, both of which are important to your business. Understanding and using color management also allows you to get the best quality out of your color technologies, regardless of the technology type. On today's session, we will mainly focus on printing, with an emphasis on some wide format printing considerations. Before you learn these valuable foundations from John Nate, we would like to take a quick poll to get to know you a little better. So you should now see 2 questions on your screen. We will give you a moment to complete these. Okay, thank you. I will now hand you over to John Nate for the main part of today's session.
Thank you very much, Carrie, and welcome everybody to our first session. The topics I'm going to cover today, kind of a high-level overview of color management, starting with what color management actually is, a definition of color management. Discussion of what color space is, how we determine or quantify color accuracy. It's a term we use called delta E. You may have heard this. I'm going to explain exactly what that means. The difference between device-dependent and device-independent color. Cover gamut. Rendering intense and black point compensations, 2 fairly important concepts that a lot of people don't even realize exist in the world of color management. Color transforms, conversions from, say, RGB to CMYK or one CMYK space to another CMYK space. The difference between calibration and profiling, and also a little bit on spot colors. So let's get going. Let's start with what exactly is color management and why do we need it? Well, the key thing to remember is color management is a process. It's not a simple task. It's not, oh, I calibrated my monitor or I built an ICC profile for my output device. It's a number of different items and really technologies working together. What it's intended to do is to ensure color fidelity, color accuracy between all of our different devices. We want to make sure that the image off of our digital camera looks correct on our monitor, and what we see on the monitor looks the best it can at representing what I'm going to get off my output device. The output device might be a proofing device, so we want to make sure the color on the proofing device looks like the color on the final production device, whether it's a wide or grand format inkjet printer or a printing press. And it is all of this working together to make sure that the color is as accurate as it can be between all of these different devices. However, there's a limitation. We are limited by each device. I'll get into that a little bit later when we talk about device-dependent color. But in a nutshell, imagine you're looking at a printing press loaded with a newsprint. Well, if you print solid yellow on newsprint, you all know from looking at the Sunday paper, you're not going to get anywhere near as brilliant a yellow as you will on, say, a large format inkjet printer. Color management understands this, and it allows us to work to try to get the best color we can, regardless of the device. To simplify things, I'd like to call upon an idea that a friend of mine, Steve Upton from Chroma, came up with, and that is color management is like making toast. Well, what do we mean by this? Well, imagine you have a toaster. You have a toaster with a knob on it that goes from 1 to 10, and you toast 10 slices of bread on that toaster. Now imagine that I also have a toaster. Take my toaster. Might be the same brand, might be a different brand, but it also has settings 1 through 10. I toast 10 slices of bread on my toaster. Well, as you can see, the toast at each setting does not match. If we slide these pieces of toast across from one another, we can find an area where we can line up how dark the slices of toast are. Now what we see here is Your toaster can actually toast lighter than my toaster can. I could possibly pop up my toast a little early, but that's not real repeatable. We have kind of an automated system here, and I have a couple slices of toast on my setting 9 and 10 that are darker than your setting 9 and 10. So we now understand the commonality of toast. We know what the capabilities are that we can get on the two machines that would match, and we know that if you on your toaster see density 5 that you like, you would order density 3 from my toaster. Now, if we measured all of these slices of bread, or slices of toast, and stored the measurement, the density of the toast, if you will, in a file, and we did the same for my toaster, we might be able to set up some type of an automated system where when you ordered 5, it automatically set my toaster to level 3. These measurement files would be a profile of how the toaster reproduces the toast density. In our world of color management, we look at all of our devices and we not only determine the density of color, but we also look at the actual color, the saturation, the hue. More on that a little bit later. But we can automate this process then where you get what you want off of my device. And that's kind of the heart and soul of color management. It also points to why we need color management, because our devices are not the same. We cannot simply send a piece of information up to a monitor or to a printer and expect to get the same result every time. It's like going down to the local Best Buy or television store and look at the wall of TVs. Even though they're all getting the same information, they do not all match, and that's because of the differences in the device. So let's take a look at some of the basic terms here. First of all, color space. Color space is often called lab color space, or LAB. You might have seen LAB as an item on a drop-down list in the creative applications. A lot of people are not sure what that means. Is that like a laboratory color space, something scientists use? Well, actually, it's a different way of defining color. And the key to LAB is it's 3 channels, just like RGB is 3 channels of light, and CMYK is a color space with 4 channels using ink. Well, LAB really means what does the color look like. The LAB channels, first let's look at L. It is 0 to 100%, and it's the lightness channel. How light or dark is the color? You can imagine it as dealing with light. 0 is no light, so that would be black. 100 is all the light possible, so that would be white. So that's the L, it's actually pronounced L star, the little asterisk is pronounced star. So that's the L star channel. Now the second channel is the A channel, and A is the red to green component of the color we're looking at. And this goes from positive 127 to negative 127, and a key is the very middle, 0 is neutral. Now if we move on to the B star, it's the yellow to blue channel. Now, of course, just to make sure that things are a little more complicated than they probably need to be, this goes from a positive 127 to a minus 128. And these numbers aren't really that important that anyone knows. It's really used as a reference when we compare two colors, not so much that you understand, oh, where is a plus 92 B star? That's far less important to understand. But again, the 0 point of the B star channel is also neutral. So those are our LAB channels, and if we take these and overlap them and kind of crisscross them so that the centers line up, we could actually wrap a sphere around them, and this is truly what color space is. It is literally a shape. Inside a computer, color is a shape, and if we want a particular color, it's a particular LAB value, which is a location somewhere in this 3D ball of color. So you can amaze all your friends tonight when someone says, is that the right color? You can say, well, I think it's the wrong location, and that's why the color is incorrect. We'll investigate this a little more as we go along. But before we can talk about whether color is accurate using a color managed system, we have to really kind of get an idea of how color can be inaccurate. And it can be inaccurate because of an error in hue, the color, chroma, the saturation, or luminance, the brightness. Let's take a look at each of these individually. First of all, hue. This is the easiest. Is it literally the right color? For most people, this is the easy one to pick out. It's did you grab the right crayon out of the box of crayons? Well, I wanted this green, but I kind of got a yellow green or a green yellow, or actually it's a red or a blue. It's physically the wrong color. A lot of people can pick out when there is a hue error. If we look at this in 3D color space, alongside the hue, saturation, lightness sliders from Photoshop, we're really talking about this slider changing the location of the color, again, in space. If we take a look at this particular sample, this green pixel, if I move the slider for hue, what I'm actually doing is moving it around in 3D color space. Okay? If you recall, the A-B channels dictate what color it is, and as we move hue, we're giving it different A-B addresses. We're physically changing where it exists, changing the hue. Is it green? Is it more of a cyan, a blue, a red, a magenta? We're just rotating it around this circle. Chroma, saturation, think of this as a can of paint. Here's the actual color of the can of paint you want. And if you physically add more pigment, you know, you go to the paint store and they have the little concentrated colors that they add to the neutral base color to give us more saturation of the color. That would be the same here. And if you could actually take the paint and run it through a filter and filter out the pigment, it would move towards less saturation, ultimately back to the base color, which is usually a neutral. That's our saturation channel. In saturation, if we again take a look at a sample color, in this case, kind of a middle red. If I move this slider to the right, or excuse me, to the left, I'm moving it in more towards the center. Remember, those center points are neutral, gray, so I'm actually removing pigment, removing color, moving it more towards a gray color or a neutral color. If I move the slider to the right, I'm adding saturation to the color. I'm moving it to the outside of color space. The outside of color space is where all the saturated colors live, especially most saturated right at the equator. Last is lightness. Here we're taking our same can of paint, and instead of adding more or less pigment, we're adding white paint to make it lighter or black paint to make it darker. In 3D color space, if we look at our Luminance channel, let's go back to our red sample. Moving to the right or to the left actually raises the color towards the top or towards the bottom. Remember, our L-star channel at the very top is white, so all our pastel colors live up towards the top, towards the North Pole, and at the South Pole is where all of our saturated colors live. So moving the lightness channel to the left moves it towards the bottom. We get darker and darker and darker greens until ultimately we get black, and moving it to the right towards the top, we get our pastel colors. Ultimately, we might even get to pure white. So moving the hue, saturation, lightness sliders simply takes a pixel and moves it to a different location somewhere in our 3D color space. If the location of the color is not accurate, meaning we are not getting the color we want, we have a color error. It could be an error in hue, saturation, or chroma, hue, brightness, or saturation. Usually it's a combination of the three. The farther away the color is from where the color should be is the greater the error. And we can actually quantify the error by calling it a delta E error. Delta E is simply how far away from the color is the color. The farther away from the color we want to the actual location in 3D color space, the greater the delta E error. In the graphic arts industry, the rule of thumb is that a delta of 1 or less means most people can't see a difference between the two samples. So that's kind of our ideal, our golden stick in the ground. We'd like to have a delta of 1.0 or less. Now, it's not a perfect scale. Grayscales we can actually see maybe down to a delta E error of maybe 0.5 or 0.6. And in some colors such as yellow, we might need even a greater color error. By the way, for any of the women in the listening audience this morning, women can see color better than men. So if guys, if you're working with a female counterpart and she tells you the color is inaccurate, believe her, because she's going to see the color more accurately than we gentlemen will. Now, you can have an error here. I've got this shown as a delta E error of 3, and the delta E error of 3 could be, again, it could be brighter, it could be contrasty or more saturation or darker. Delta E7 is even going to be a greater error. The standards, and we're going to take a look at standards in the next session in 3 weeks. A lot of the standards list the quality of the output as average and peak delta E, and this is where this comes from. The peak delta E is the one worst color. In North America, we often go by what the ID Alliance governing board says, and the peak delta E should be 6 or less. The average delta E, looking at all the colors, should be 3 or less. So again, we'll get into more in this in 3 weeks, but delta E is kind of what we live and die by as far as color accuracy. Now, the reason we need all this is because of what we call device-dependent color. The color we get depends upon the device. It's as simple as that. If I have 2 cameras, might be one right after the other off the assembly line, in a studio, controlled lighting conditions, aimed at the same apple, and I take a photograph with each camera and open it up in Photoshop and sample the exact same pixel, I'm likely to get 2 different RGB values. Well, why? Well, because the cameras are not identical. The sensor on the back of the camera that actually captures the image, they're going to be a little different from one manufacturing batch to the next. The lenses, the actual optics are going to be slightly different. The mechanical part, the shutter speed, the f-stop, going to be slightly different. All of that combines to give us different color. So what color do you get? It depends. It depends upon the device we're using. The same goes with our output devices. I could have 3 different output devices, or the same output device maybe with different media. So I've got photogloss, semi-matte, and canvas. Well, to reproduce the apple correctly, we look at that same red pixel in isolation, I might need 3 different recipes, one for each output device or one for each media in order to get the color correct. Why? Because the color depends upon the device. The media absorbs ink differently. The printer prints out color differently, whether it's toner, whether it's ink, or whether it's ink on a printing press. They're all slightly different. Now, I know that they match because if I get the same LAB value when I measure the 3 pixels, if those 3 pixels match, I know it's going to look the same to the human eye. Remember, that's where LAB comes in. It's what it looks like. So if the LAB values are the same, even though I need different recipes to get there, it means that the color will match. So LAB is device independent. It doesn't care what device, doesn't care whether it's a monitor, a camera, a wide format, a small desktop printer. If the LAB values match, it will look the same. Well, now let's talk about Gamut, because that is a limiting factor in a lot of our devices. Okay? If I have, imagine a color is the size of a marble, and every color I can reproduce, I put inside that color space, that ball of color. The more colors I can reproduce, the larger an area it's going to take up. This is increasing the gamut. So the more marbles, the more colors you can reproduce, the larger the gamut. But you have to be a little careful with this. Let's delve into this a little deeper, because it's not simply how many marbles you've got in the sphere of color space. If I have a fairly light burgundy and a dark burgundy, if I can now have a color in between those two, well, I haven't increased the gamut. How about here? I've got 3 colors I can render in between my light burgundy and dark burgundy. Again, that did not increase my gamut. This increased the gamut. I can print lighter or darker. Okay? So just being able to address additional colors in between any 2 colors doesn't increase the gamut. Oh, it might give you better gradations, smoother gradations, but it's not going to increase the gamut. To increase the size of color space, increase the gamut of our device, we need for instance, a whiter media. We need to be able to print darker or print more saturated. That's what gives us the larger gamut. Well, let's look at some common color spaces actually displayed in 3 dimensions. This is swap, one of the most common color spaces we have in the world today. Swap is a very common default color space in the Adobe applications, and this is the swap profile displayed in a program called ColorThink. ColorThink is a program from Steve Upton's company Chroma. And you can see at the base here the size of the gamut of the color space. This is kind of the maximum perimeter of the color space. Now let's take a look at Grackle overlaid. Grackle is a little bit larger. So Grackle contains all the color that Swap does, but Swap does not contain all the color that Grackle does. That makes sense because Grackle is printed on a little better stock, a little more ink. Also, top to bottom here, I hope you can see this, but the Grackle is a little overall larger top to bottom, which means the Grackle paper is a little whiter, and below it can hit a little darker tone than can Swap. Well, how about my inkjet printer here in my lab? Well, you can see my inkjet printer is much larger than either Swap or Grackle. That means if someone wants to have a print that conforms to Swap or Grackle on my inkjet printer, I can easily hit that. I am much larger all around than Swap or Grackle on my inkjet printer. I have much more gamut that I can work with. However, if someone said, well, I want you to print on this Grackle device and I want you to simulate this inkjet, obviously that we can't do because there are many colors that are, is what we call it, out of gamut for the output device. Swap and Grackle can't give us all of these more saturated colors from inkjet. How about Adobe RGB? Look at one of the RGB spaces. Even larger. I mean, it's huge. It's not the largest. ProPhoto is probably one of the largest, but Adobe RGB is pretty large in and of its own right. And it can give us much more color, but not in yellows and oranges. My inkjet printer can actually give a little more gamut in the yellow and orange area than Adobe RGB. So you can see no color space is perfect. There's always going to be limitations. Now how about toner? If we look at the Swap color space, and remember Grackle is just a little larger, and our toner systems, our toner printers have gotten much, much better over the years. They used to have much, much smaller gamuts than the inkjet printers, but they're doing quite a good job of catching up. So on my toner-based printer, I can also easily simulate Swap. So if someone needs to match Swap across the entire output range from brochure to displays, we can simulate that on our toner device or on our inkjet device. I've got here an image of a device with a very, very large gamut. Perhaps this is my digital camera. This is the color I want to reproduce. I want to reproduce that brilliant bright green on this output device with a much smaller gamut. This might be an inkjet printer that I'm running with a fairly low-quality stock. Well, where exactly does that green live over here? As you can see, it doesn't exist. So I have two options. I'll ignore that pixel. I'll just use paper white. If I can't print that pixel, I won't print that pixel. Customer's probably not going to be real pleased with that output if he sees all these holes in the final output. So what we have to do is we have to remap or change the address in 3D color space from this green to a green that actually is a green that I can reproduce. And to do that, we enter the world of rendering intents. Now, spot colors are probably one of the most commonly recognized areas where gamut rears its ugly head. In an ideal world, spot colors are printed with exactly the color of ink that the color is supposed to be. Often we use cyan, magenta, yellow, black, or additional inks on some of our inkjet printers to try to accurately render that color, even though we don't have that specific color of ink available. And if you stand a far enough distance away where the dot pattern kind of blurs, you can get, in many, many cases, a color that is a fairly accurate representation of what the spot color should be, but not always. Any of you that are familiar with the Pantone Bridge book, if you look at that, there are two patches for every color. One color is the specific color of ink printed. This is what the color is supposed to look like. The second half, the not so attractive half of the Pantone Bridge book, shows us what the color will look like as accurately as Pantone thinks we can get printing on a 4-color press. Now on our inkjet printer or our toner device, we might be able to get more accurate than we can on a printing press because we have a little more gamut to play with than we do on most printing presses. But as you can see, this color just may not be acceptable to many print buyers because of the problem of the gamut of our output devices. So with some of that background information, it's time to make decisions, especially in our applications. The first is selection of rendering intent. Now, you might wonder what rendering intent is. As I mentioned before, it's how we remap or relocate colors in that three-dimensional color space to become a color rather than one we can't reproduce to one we can reproduce. This is a top-down view of 2 ideal gamuts. If you remember from the 3D views, they're actually far less than perfect spheres. But a smaller gamut device, maybe this is my inkjet printer, and a larger gamut device, perhaps this is my digital camera. And I photographed an image, and I've isolated 6 specific pixels. 3 pixels are out of gamut. These colors do not exist in my destination space, my inkjet printer. 3 pixels do. I can actually reproduce these colors on my output device with no problem. Well, what do I do with the out-of-gamut pixels? Enter the rendering intents. The first is perceptual. Now, I've kind of zoomed into that area where these pixels are. We can see the 3 pixels that are in gamut and the 3 pixels that are out of gamut. So what perceptual does is it will take the largest, or the farthest out pixel, the maximum, say, saturation that we can print, and it moves it in to become the most accurate color it can reproduce, that farthest out pixel of my destination space. Pixel 5 moves a little farther in. It tries to keep this relationship, okay? Pixel 5 is a little farther in on my source. Pixel 5 should be a little farther in on my destination. What about Pixel 4? It should also move in a little farther. So you've noticed I've kept the relationship consistent. Well, gosh, now Pixel 3 is kind of in the way here. So we need to take pixels 1, 2, and 3 and move them in also. We're moving towards the center of color space, so I'm actually losing saturation on all my colors. But what you can imagine here is we've taken this entire large ball of color and just simply evenly crushed it to fit within the output device. If we take a look again at these out-of-gamut pixels, they get moved into gamut, but the relationship is kept the same. So from my original 6-pixel location, I have my new 6-pixel location, and you could make the case that, well, I've now screwed up all the color. I've messed up all the color. And you actually would be accurate. We in that statement, we have actually changed all the colors. But note the term perceptual. You won't perceive that there was a color difference because we've kept everything, we've kept all the relationship, we've kept everything proportional. It would be, oh, imagine you have a photograph in front of you and you put on colored sunglasses. Colored sunglasses are yellow. And everything goes yellow, but our mind can kind of play tricks on itself, and after a short period of time it kind of knows what the white area of that image is, and pretty soon, even though you're wearing yellow sunglasses, everything kind of looks correct. Okay? Then you take the sunglasses off and everything looks blue for a while until your mind relaxes and corrects for that. Well, imagine if you put on those yellow sunglasses and only highlights changed. The rest didn't. Well, you would always notice that there's a color problem. So that's the idea here. Since we changed everything, nothing sticks out as being an error. And that is the perceptual rendering intent. Most often used for RGB to CMYK conversions, but I want to caution you, it's not because they're converting from RGB to CMYK, it's because usually RGB is a much larger color space than CMYK, and we want to use perceptual to make sure that we keep relationships correct. Next up is colorimetric. Colorimetric is often listed as the most accurate rendering intent. It's the most accurate because if pixels are able to be accurately reproduced, it will leave them alone. And pixels that are out of Gamut, it moves each one the minimum amount it needs to. It remaps them the smallest amount in order to be able to reproduce them. So it does not keep relationships, okay? It treats every pixel, every color individually. Now, what just happened if I had a gradient or detail in this area? I've now banded this area. All of the color in this area has been what we call clipped or compressed. So I've lost any definition in this area. That's the danger of the colorimetric rendering intent. But it is the most accurate. It's also the default in our applications. Now, one of the reasons it's the default is because it's technically the most accurate. The second reason it's the default is if it's the incorrect rendering intent, and it's incorrect because you've noticed loss of detail in saturated colors, you'll be able to see that. If perceptual is the incorrect rendering intent, well, you maybe gave up color that you didn't have to. What if you didn't have pixels 4, 5, and 6 in this image? You only had pixels 1, 2, and 3, but it was in a large color space. Perceptual would still move pixels 1, 2, and 3, and I'd give up some color that I didn't have to. But you only knew that if you did a conversion both ways and compared the two. Colorimetric, you should know right away by examining these saturated areas and seeing if you've lost tone distribution, you've lost drawing, you've lost detail. Last up, saturation. Hardly ever used in the graphic arts industry. In saturation, pixels 4, 5, and 6 are treated just as they were with colorimetric. They're all remapped the minimum amount they need. I've potentially banded the colors the same as I did in colorimetric here. But saturation rendering intent moves pixels that are in Gamut a little towards the outside, towards the saturated areas. Remember, in our 3D ball of color, the equator is where the saturated colors are. So they move towards the endpoints of the saturated areas of color space. This could be used maybe for business graphics, cartoons, comic books, things like that, where you're dealing more with circusy kind of colors and you want to keep them nice and brilliant. Very, very, very rarely seen used in the graphic arts industry, however. So mainly we're working with perceptual and colorimetric. Now, colorimetric actually has two flavors, relative colorimetric and absolute colorimetric. And you can see these on the drop-down list in Photoshop and Illustrator and CorelDRAW and all of our creative applications. The difference between relative and absolute colorimetric is absolute colorimetric understands the white point of the media. It is only ever used in proofing. And if you use absolute colorimetric, you will simulate the white point of the reference on the destination. Let me clear that up a little bit. I'm printing on my inkjet printer, but I want to simulate an image that's going to print on newsprint. If I use absolute colorimetric, I actually simulate the low-grade newspaper stock on my output device, where relative colorimetric left the white point of my inkjet printer media intact. So this looks much better. If I'm trying to simulate newsprint, I'm going to use absolute colorimetric in order to really get a good representation of what the output's going to look like. So absolute colorimetric normally only used when making proofs. Give you a little better idea of this issue of banding of these saturated colors. Imagine I've got a gradient here from 0 to a pretty deep red color. And let's say this is the maximum red my output device can reproduce. Okay, I'm exaggerating things here for clarity. And I can reproduce using the perceptual rendering intent or the colorimetric rendering intent. If I use perceptual, I've taken this maximum red that can be reproduced on the output device, and I've moved it to the endpoint, and I've made a gradient from 0 to now this point. In colorimetric, I have simply taken this maximum level and moved it down, and I've kind of kept it in position, and every tone that's darker simply gets compressed and becomes that same tone. If I take this tone and make a rectangle and overlay my two rendering intents, you can see I still have tone distribution using perceptual rendering intent, but in colorimetric, I have absolutely no detail through this entire area of my image. That's why you want to look at the saturated color areas and see if you're losing detail, because that's where you're going to notice it. Another item that we have to select is black point compensation. Black point compensation is a lot easier because it's either yes or no. Black point compensation deals with the fact that some of our output devices can print, well, to simplify things, they can print darker than other output devices. If I take a look at Adobe RGB, I can go from 0 L-star, pure black, to 100 L-star, pure white. Well, that's a theoretical color space. Our actual devices really all fit within that. They can't hit 0 to 100. But my inkjet printer in my lab, I can get down to L-star value of 4. I can print very, very dark. And L-star 93, well, that's the limitation of my media. That's as bright as my media is, a 93 L-star. Now let's say I've got an image that I converted to look good on my inkjet printer. And now I'm going to send it to the newspaper to be reproduced. If I convert from my inkjet profile to my newsprint profile and I say black point compensation yes, it's going to compress. My maximum black level will become the maximum black level. And I'll keep the tone distribution. This is just like the perceptual rendering intent for color, except we're kind of really dealing with just overall density. If I say black point compensation no, it takes the darkest tone that I can reproduce, and it makes every tone that's darker than that same tone. So I've compressed my tone values. This is much like the colorimetric rendering intent. Now, how about if I'm going the opposite direction? I've got an image that was converted to newsprint, and I'm now going to print it on my inkjet printer. If I say black point compensation yes, it will expand the tonal range somewhat and be able to take advantage of the fact that I can print darker on my inkjet printer than a newspaper can print on their newspaper media. If I say black point compensation no, it simply prints that darkest value, L-star value 35, and we all know how dark a newspaper looks, not very. That's how dark it will be on my inkjet printer. Now, which one is correct? And a lot of people say, oh, well, A is going to look better. In the world of color management, be very careful about using a term such as looks better. In the world of color management, usually it either is accurate or it looks worse. Someone might say, I like the result better, okay, but saying it looks better is a little different. If I want to make a proof on my inkjet printer for the newspaper, and I use A, black point compensation yes, well, you might say, well, that's going to look better. Yes, but it's not going to look like what the newspaper will look like. And if I actually made a proof with black point compensation yes, I'm going to have more of a tonal range that they're going to be able to reproduce on the output. And when my customer goes to press check or gets their Sunday paper, they're not going to be real happy. So in the world of proofing, black point compensation is normally off. In the world of production printing, black point compensation is normally on because it can give us better shadow detail. And if the final product is the product coming off of our grand format inkjet printer, hey, if I can give you better shadow detail, that's going to be an image that you think looks better. It may be less accurate compared to a printing press, but if I'm not trying to match a printing press, I don't care. I can give you something that's going to be a better reproduction of the original. Okay? And that's kind of a key item with color management. We're trying to change the image the least amount possible as I move it through the stream, from the digital camera to the monitor to the proofing system to the output device. Try to change it as little as possible. I teach some courses in color management, and I often tell the students that if you have an original that looks awful, just awful, and you bring it through a color managed workflow and you print it, and you look at the print and it looks awful, congratulations. You have accurately reproduced that within the limitation of the devices. That's what color management should do. It should not improve the image or, as someone will say, fix the image, because color management doesn't know that images are broken. It assumes that whatever you feed it is correct. All right, taking a look at black point compensation, kind of the real world here, I have an image opened up in Photoshop. I did a couple screen captures. And if you go to the custom proof setup, there is a checkbox for black point compensation. Here, that checkbox is unchecked. Here, it is checked. So this is black point compensation on. And I hope you can see on your monitors that I have much better shadow detail on the bellows of this old camera. I have better detail in the dark blue towel here in the background. However, my highlights, my middle tones, they look the same. So it really impacts shadow areas the most. Taking a close-up look, this is what you will see if you go to the custom proof setup, this black point compensation checkbox. Turn it on or off. With the preview would normally be turned on if you want to actually view it on your screen. But with the preview turned on, toggling black point compensation on or off, you'll be able to see the retention of that additional shadow detail. Also, switching rendering intents, you'll be able to see, especially in the saturated areas, what's going to happen to your color. We have to set these options in our default, as the defaults in our programs, or, well, some engineer in a basement somewhere has decided for us. This is the color settings panel in the Adobe Creative Suite, and if you click on the More Options, the button then turns to Fewer Options, but if you click the More Options button, the bottom half of this panel will appear, and this is where you select the rendering intent and whether you want to use black point compensation. In my classes, if the students are in on the first day and they have their laptops, I ask how many have Photoshop. And then I ask them, what is the default rendering intent you have selected? And they look at me with these blank looks on their faces, and they say, we don't know what that means. And I say, oh, relative colorimetric. Okay, thank you. Do you have black point compensation on or off? And they say, what's black point compensation? I say, oh, black point compensation is on. Thank you again. And they say, what do you mean? I said, okay, launch Photoshop, go to the color settings panel, go to the More Options, and look down below. What's your rendering intent? And they obviously just stare at me in awe and say, it's relative colorimetric. How about black point compensation? Well, it's turned on. And they say, how did you know that? And I say, it's simple. You didn't. Since you didn't know what they were set at, that meant you didn't even know you could set them, which meant they were probably still at the defaults. Now, is that correct? Relative colorimetric. I'm a photographer. I'm converting from a very large color space with a lot of saturated colors to my destination, my output, my inkjet printer. Relative colorimetric is probably not the correct option. I'm making proofs. Black point compensation on is probably not the correct option. So we need to take charge of these settings in our programs. And they're used in many different areas, okay? We need to select the proper working space. What am I going to use as my default profiles? What are my default settings for relative colorimetric for black point compensation here in the Adobe Suite? But also when I'm opening up images, I have to answer questions. What profiles do I want to use? Do I want to do conversions? Do I want to assign a different profile? What does all this mean? Well, assigning a profile or converting a profile, remember the profile is the recording of how a device reproduces color. I'm going to get into a little more detail here in just a bit on that. But assigning changes the way an image looks or prints, while converting keeps the look the same. Now, that may seem a little counterintuitive. You would think, well, if I'm converting something, I'm changing it. Well, you're changing the recipe. Color is based on recipes, amounts of red, green, blue, light, cyan, magenta, yellow, black ink. When I was growing up on a farm in northern Wisconsin, we had the spice salesman, the Watkins man, who would stop by our house, every 6 months or so, and sell my mother spices. So she would buy her spices in bulk because at that time there just weren't really many spices available at the local store. Well, imagine she bought her chili powder a year ago, and I go to the store and I buy my chili powder fresh because I like my food a lot hotter and I want to use fresh spices. Well, if I assign the value, the recipe, it's 1 tablespoon of chili powder in this recipe. And if I simply assign it, yes, use 1 tablespoon of chili powder, I've assigned my mother's ingredients, in this case a spice, but on an inkjet printer, amounts of cyan, magenta, yellow, black ink. If I assign the same values, I'm going to get a different result. It's back to that device-dependent color. Okay, so simply assigning, well, my mother's chili is not going to taste like my chili. I might have to convert. I have to convert my spice to the capability of my mother's spice, or my red inkjet ink to the red inkjet ink from this other output device. Oh, but this other output device has magenta and yellow. It doesn't have red ink, so I might have to come up with a completely different recipe. But 1 tablespoon of my recipe, 4 tablespoons, actually probably the entire box of spice, as old as my mother's spices got, in order to get the same taste. So again, converting gets the same result. Assigning changes the result. Let's take a look at this in our world. I've got original color here, a dark burgundy, that's in the Grackle color space. Okay, the Grackle profile has been assigned to this image in Photoshop. Here is the recipe. 23 cyan, 92 magenta, 53 yellow, 17 black. That gives me this LAB value. And, class, what does LAB mean? What is it going to look like? So this recipe in the world of Grackle looks like this. Let's say I'm going to change this to swap. If I assign the swap profile, I keep the recipe. Remember, just like my mother's spices, assign it. Use 1 tablespoon of my mother's spice. Use the same amount of cyan, magenta, and yellow, and black ink. I get a different LAB value. That amount of ink on a swap press is going to look different. Well, what if I did a conversion? If I did a conversion, it's going to say, this is the LAB value I want. And it's going to say the LAB value has to be correct on the output device, so come up with a new recipe. So assigning keeps the recipe, converting keeps the result, what I want. If we look at some images, I've got an image in Grackle, and if I converted it to swap, if depending upon how the gods of WebEx are treating us today and how good your monitor is, you should be able to see that there's less saturation in the brilliant colors. Okay, I've lost some saturation because swap, if you remember back to our 3D images, has a smaller gamut. It can't contain all those colors. This, by the way, is also in these saturated areas where you would start to look for banding or loss of detail using the relative colorimetric rendering intent. Okay, another comparison, here is my image converted, same output within the limitation of the output device, and here I've assigned 2 different profiles. Now this profile, assign it, which means change the way it looks but keep the recipes, it's a little darker, it's a little more saturated. And this profile, it's much redder. My neutrals are all gone. I've lost detail. So assigning radically changed how the image is going to look. Converting tried to keep it the same. Well, in order to get accurate color, we need to work with calibration profiling on our output devices, or actually our input devices too. Calibration itself is active. It physically changes the device. It is used to match a device to itself over time so that I get the same results over time, same today, tomorrow, last month. It tries to bring the device into a repeatable state. I want to get the same results, so if I'm doing a reprint, I know I can match the color. It's like tuning a guitar. If you and I each have guitars, but they're not tuned the same and we're in the same room, we're trying to play a song, we're not going to match. There's just no way we can. But if we tune the guitars and we play the same song, well, then we blend. Then we're going to sound the same. Now, calibration is sometimes called linearization, but it really is only one part of calibration. If I take my new high-end digital camera here, and I want to do a calibration, calibration on a camera is done by setting shutter speed, aperture, and on better cameras, setting the white or gray balance. This is probably one of the most important aspects of doing effective calibration on a camera. Shutter speed and aperture are going to define whether I have highlight detail or shadow detail, but white or gray balance makes sure that the color is as accurate as it can be. On a monitor, I want to set brightness. I can on pretty much any monitor. Contrast, on some of the better monitors we can set contrast. My laptop I can't, but on the real good monitors we can also set the white point. What color is white? Now this may sound strange the first time you hear it, but imagine white outside on a sunny day. The sun is very blue, but a white sheet of paper under a tungsten light is very yellow. What white point am I trying to hit? Am I trying to hit the color of white of my media on my output device? Possibly. That's where calibration of monitors comes in. Now on our output devices, We might have a small or a large format inkjet printer here. Let's actually make the relationship a little more accurate here. And I did this on purpose because I don't care which output device and what size it is, whether it's an inkjet printer or a toner device. Calibration is calibration. Some tasks are not performed on, for instance, toner devices, but the concept is still there. First, per channel ink or toner limits, per channel linearity, total ink or toner limits, and ink gray balance. Now, these are often done through the use of a RIP because there's very seldom some great big red button on the side of your inkjet printer that says, calibrate me. Now, inside our RIP, we will print samples. For instance, here's a gradient of cyan, magenta, yellow, and black. I'm working on the per channel ink limits. Often this is done by the manufacturer of the toner device, but on an inkjet printer, we likely have to do it ourselves. And if I look at these outputs, this is an aqueous, a water-based inkjet printer. So right at this point, that much cyan ink, any more than that, and the paper's coming out wet. At this level of magenta, any more, and I'm not getting any more saturation. It's not wet, but I'm not gaining anything. Same with yellow. And on my black ink, again, at this point, it's wet. So I can say 92% is the maximum ink limit for cyan, 89 magenta, 96 yellow, 81 black. Any more than that, and it's either coming out wet or I'm wasting ink. On a UV inkjet printer, or a toner-based output device, you would be simply wasting toner or wasting ink. If you're on a toner-based system or a UV inkjet printer and your material is coming out wet, you're probably going to have to call the service people in because there's something desperately wrong. Now, once we have our per-channel limits, we want to have per-channel linearity. Here, on my black channel, I've got very little change from 0 to 75% and then a big change. This is going to be hard to control. Here I've got the opposite, a very fast change from 0 to 25% and then not much change. Again, difficult to control. They are non-linear devices. What I want is a nice, even gradation throughout the tonal scale. Total ink limit, fairly easy. I print out patches, maximum 400%, 100% each of cyan, magenta, yellow, black, all stacked on top of each other. And I notice past 340%, it's no darker. Well, then, 340% is my total ink limit. On my aqueous inkjet printer, I notice that past 320%, the ink comes out wet. It's not dry. Then 320% is my total ink limit. So we'll look at total ink limit based on I'm not gaining anything, I'm just wasting ink, or my media is coming out wet. And finally, a gray balance. On inkjet printers, we want to try to set a good gray balance. Here's a poor gray balance. It starts neutral, goes magenta, then green. Here's, well, questionable gray balance. It starts at white and it goes through kind of a yellowish cyan. But it's at least even through the tonal range. But this is what I want, nice, good neutrals through the entire tonal range. And all those together give me my calibrated state. Now, on top of that, I build a profile. I print sample images or sample patches, measure them, and I build an ICC profile. ICC is the International Color Consortium. It is the body of industry manufacturers, representatives of the industry, and they've determined how to define or quantify how a device prints color, and that is through the use of these ICC profiles. The profile is passive. The profile can't give you better color than the device can, or we'll say it works within the limitation of the calibration. Okay? It's a snapshot of the device characteristics. It just tells us how the device reproduces color. To build one, I would send, now here's a sample of just 5 patches. In true life, if I'm profiling an output device like an inkjet printer, I might print 1,000, 1,500 patches, maybe even more. But I send recipes, CMYK values, to my output device, and I measure them with something called a spectrophotometer and get LAB values. What color does this recipe look like on this output device with this media? Well, then if I take, let's say, that same red, and here's the recipe that I printed where I sampled it and got this LAB value, 0 cyan, 100% magenta, 66 yellow, and 0 black. And that happens to be the color of that red pixel way back at the beginning of the presentation. What I want is that same LAB value. So I've built an ICC profile for each of my 3 output devices or each of the 3 media on my single output device, and the ICC profile is going to take the LAB value I want and convert it to a recipe for that particular output device, the combination of device, ink, and media, that's going to reproduce the pixel accurately. That means that that pixel on these output devices through their own profile will give me that LAB value, and I will have accurate color reproduction. Which brings us back to our color management is like making toast. We know the density of toast. We know the LAB value I want. A profile will convert it to the correct recipe within the limitation of the device, within its gamut, to give me the output that I want. Carrie, back to you.
Thank you, John, for that excellent presentation.
You're welcome.
So what did we learn today? We learned that basic color management concepts apply to getting the most out of all types of color technologies, and that you need to take charge of your color management settings and options. If you don't, the default settings will take charge and will likely not be the right ones for your environment. We also learned that color management is not a single task, rather a complete process, and attention needs to be paid to all aspects. If you would like to learn more, we have some resources for you. We have 3 documents from EFI. We have EFI's ABCs of Color, plus the 2 articles mentioned earlier by John, one on rendering intents and one on black point compensation. ColorWiki is also a useful resource for things such as a glossary of color terms, plus you will find some very comprehensive color management guides on xrite.com. And the PDF of today's presentation that you will receive contains live links to the websites mentioned. So we have additional World of Fiery webinars. Today we covered color management fundamentals. As mentioned previously, today's session was the first of our 3-part color series for wide format printing, and we look forward to seeing you on the following sessions too. On June the 17th, we will cover color standards and specifications, where you can gain knowledge of the latest industry standards and how they apply to wide format and super wide format printing. Then on July the 8th, we will cover color management inside Fiery XS and Fiery Pro Server, allowing you to put your knowledge into practice and understand RIP-level color controls. And we also have our production series for wide format printing starting this September. And you can register your interest for these sessions on the World of Fiery webinars homepage.
All right. Well, there was a lot of content. I know that we're close to the top of the hour. John and Carrie, if you guys can stay 5 or 10 minutes, we'll see how we do with questions here. Let our audience get some of their questions answered. We'll go over just a few minutes. As our presenters are looking at the questions already submitted, I want to make sure everybody remembers that we did record. We will send out a follow-up email within a few days with links to the recording, the presentation, all the resources. And if we don't get to your question, we are going to compile an FAQ document and provide that as well so that everybody can benefit from the great questions and answer phase that we may only have a minute or 2 for. So Carrie and John, let's get going and see how many questions we can get in just a few more minutes.
Okay, thank you. So the first question, John, is how can I color manage my printer if I don't have a RIP?
Well, if you don't have a RIP, you're going to be using the driver that the manufacturer supplies. And in a driver, when you select the media that you're going to be printed on, such as a plain paper or a gloss photo, you're actually selecting in the background a calibration file. And the per channel limits, the gray band, all of that is done in the background. So you don't normally then worry about the calibration portion. The manufacturer has taken care of that for you. All you need to do is build an ICC profile using that specific setting. You can use a product such as EFI's Color Profiler Suite. There are many consultants around that will do this for you. Chromix also has a facility where you can work with them to build remote profiles for you. So you've got a lot of options for building profiles. Once you have the profile for that output device, that media, then you can use it in conjunction with something like Photoshop or InDesign or CorelDRAW to properly color manage the output through the driver. So the driver takes care of calibration. You would still need to take care of the ICC profile.
Okay, second question. Is it possible to white balance images on an iPhone?
You can purchase apps for both the iPhones and for the Androids that will allow you to do white balancing. Some of them have simply a slider where you move the slider up and down or back and forth and look at the screen to determine what the white balance should be. Others on the high end, just like the my digital camera, I will point it at a gray area and tell the camera that that is supposed to be gray, and it will actually white or gray balance on something that I know is neutral. So with add-on applications, if you just do a web search for iPhone or Android photo app white balance, it'll usually show you the higher end applications that will allow you to do that.
Okay, thank you. And how does the file format impact color management?
In the olden days, much more than it does now. In our current applications, we can often save the profile, that ICC profile embedded in the image, and that is often, and I say often, not always, but often very important, because if you save, say, a TIFF file or a JPEG file out of Photoshop and embed the profile, when I open it up in my copy of Photoshop on my color managed monitor, my copy of Photoshop will recognize your embedded profile and render the image on my screen as accurately as it can so that I know what you probably saw on your screen and what you want on the output device. PDF files, most of the common files we now use can honor embedded profiles. The only area you would likely not use embedded profiles is on websites. They can greatly increase the size of the images, and since most people on their web browsers do not have color managed monitors, well, they really can't take advantage of the color management capabilities that we have on the web. So all you're doing then is slowing down your websites. But for everything else, pretty much the majority of the file formats that we use in the graphic arts industry can support ICC profiles.
Okay, we have a question. When I'm creating a profile, when I'm creating a profile, what rendering intent should I use?
When you build a profile, you're just simply setting the default rendering intent. However, in all of our applications, we have to select the rendering intent. That seems to be kind of a holdover from the olden days when we weren't sure whether there were going to be rendering intent selectable within our applications. Inside any ICC profile that's built, it has tables that understand the perceptual, the saturation, and the absolute and relative colorimetric rendering intents. We always have to pick them, whether we're in Illustrator, CorelDRAW, Photoshop, any of our creative applications. Now, if you use something such as, perhaps Microsoft Word or Excel or something that's normally not seen as a graphic arts program, if you could figure out some way to shove a profile, down its throat, well, maybe then the default would be used. But in our standard graphic arts applications, it really is a moot point. It doesn't matter because we always override it.
All
Okay.
Right, so I think that to respect everybody's time, let's take one more question. I know we have other questions that are coming in, and as promised, we'll get back to people individually as well as compile one FAQ document so everybody can benefit from the questions and answers. So Carrie, one more question for today, and we'll close it off.
Thank you. Somebody would like to know, what is the perceptual absolute rendering intent in Fiery XF?
Perceptual absolute in Fiery XF, I'll get into a little more detail in that in 6 weeks in the third session. But it it was really a request from a specific customer that had some specific needs. In absolute color, in absolute rendering intent, you're trying to match the white point. In perceptual, you are trying to work with a gamut that the original gamut is much larger than the destination. Well, it's incredibly rare that you would have a source color space that is much larger in color gamut than the destination. However, it also at the same time has a darker white point. But there are some specific areas where it could be of value in some RGB conversions. I'm actually going to have some samples where I'll show in the third presentation. So I guess I'll pass that off for 6 weeks and say tune in 6 weeks and we can delve into that in a little more detail, because that is kind of an obscure rendering intent specific to Fiery XF and Fiery Pro Server.
All right. So again, apologies to those of you who had questions and we couldn't get to. We're already over time. Lots of great content. I want to thank our presenters, both Carrie and John, and I want to thank our audience for joining us today. And we look forward to seeing you again in 3 weeks and then again in 6 weeks for more great information about color management. Take care.